In this video, we'll be studying a rare breed of fish called the sillyfish. Here's a sillyfish right now. Sillyfish are born in these square lakes. Specifically, they're born in the lower left-hand corner of these lakes, and their only goal in life is to reach their final resting place, which is the top right-hand corner of the lake. And they would like to collect as much food as possible along the way. Now, every day of a sillyfish's life, it can either move one move upward, one move rightward, or one move diagonally in this direction towards getting to its final resting place. Notice that it can't move left, it can't move down, it can't move diagonally in the other direction because that would mean moving away from the final resting place, which is not what they want. Furthermore, they're called sillyfish because even though it says how much food is in each square, they don't know that, they don't understand that, and every day they just make a random move in any direction that's possible. So for example, this infant sillyfish right here, who's sitting here just born, has their first day ahead of them. So randomly, they'll either move to the 1, they'll move to the 2, or to the 3. And depending on where they move, that's how much food they get. Now, another thing about sillyfish we should know is they're extremely selfish and they'll leave their own kind behind without even thinking about it. So let's see what I mean by that by an example. Let's say we have 90 sillyfish, all just infants born on the first day, ready to go on this lower left-hand corner. So we find that since there's 90 of them and they have an equal chance of going to the 1, the 2, or the 3 square, we find that 30 of them go to the 1 square. So in the parentheses, we'll put how much food they got on the first day. We have that 30 of them end up on the 2 square, and we have that 30 of them end up on the 3 square. Now, sadly, what happens is that each day, the top 50% of the sillyfish will leave the bottom 50% behind, unfortunately, to die. So the top 50% here include these 30. So there's the 50% will be 45 fish. Since there's 90, half of them is 45. So these fish fall in the top 50%, and half of these fish fall in the top 50%. So we have that 15 of these fish survive, and all these fish survive, but all of these poor fish who just randomly decided to go to the 1 square are left behind. So we have in the next generation, we have 30 fish who are able to get 3 pieces of food, and 15 fish who are able to get 2 pieces of food. Then breed amongst themselves and double in size. So these 30 fish become 60 fish. And I'm going to put a 3 here, and I'll tell you why. And these 15 fish that were also taken become 30 fish who are able to get 2. So notice now, we had 90 fish in the beginning. All 30 of these fish who are able to get 3 pieces of food are taken and double. And 15 of these fish who are able to get 2 pieces of food double. So we have, again, 90 fish, just like we had in the beginning. The difference is these 60 fish know already how to get 3 pieces of food. They have it kind of ingrained in their genetic programming, in their instincts. They know exactly what to do to get these 3 pieces of food. So that means that they know already to go to this 3 square. They don't need to do it randomly. But after that, they have no idea what to do. Similarly, these 30 fish right here know how to get 2 pieces of food. They know, starting from birth, that they can go ahead and get 2 pieces of food, but they don't really know what to do after that. So it's kind of like natural selection, and that's exactly what we're going to go into when we talk about genetic algorithms. This is all just a genetic algorithm. We'll just give it a name a little bit later on. It's really just natural selection at play. It's that the top people, the top fish who are able to get the most food, they end up reproducing and creating, passing on their adaptations, so basically their ability to know how to get the most food, to their offspring. And from there on, their offspring have to make their own moves. So we again have 90 fish. So let's just keep going and see what we get. So we have 90 fish, 60 of which know how to get 3, and 30 of which know how to get 2. So now what happens with these 60 fish? So right now they know how to get to this point. Now they have 3 more moves they can make, right? They can either go to this 2, they can go to this 2, or they can go to this 3. So this group of 60 is again going to split into 3 groups of 20 each. So we're going to have 20, 20, 20. And some of them are going to go over here, get lucky, and get 3 more. So these people, these fish, know how to get 6 total. They know how to go here and then go here. So they're going to get 6 total. 20 fish know how to get 5, and the other 20 fish also know how to get 5, just a different route. So 5 and 5. Now what about these 30 fish who are able to get to this point? They also have 3 options, right? They can go to the 1, the 2, or the 2. So we can split them into groups of 10, because 30 divided by 3 is 10. These 10 fish know how to get another extra piece of food, so they can get 3 total. And the other 2 groups know how to get 4 total, just 2 different ways. Now we repeat the process. In this next generation, we again leave behind the bottom 50% and take the top 50%. So who are the top 50%? Well, these people who know how to get 6. How many fish will be in the 50%? Again, it's 45 because we have the same sizes up here. So we have these 20, and then we have these 20 because they can get 5, which is more than all the other groups besides the 6. So far we have 40, and we need to get an extra 5. So we're going to take 5 fish from this 5 group right here. So notice that this 30 group, this group of 30 fish who were initially able to get 2 is completely eliminated because none of the members were able to get as much food as these 60 fish. So this group, we'll do it in red to just kind of highlight it. this group is completely eliminated, and even part of this group is eliminated. We had 20 kept, but 15 of these 20 are also eliminated here. So now what do we have? We can go through more iterations, but the idea is kind of becoming clear, right? It's that we have 20 fish who know exactly from birth how to get 6 pieces of food. We have 20 fish who know exactly from birth how to get 5 pieces of food. And we have 5 fish who know exactly from birth how to get 5 pieces of food in a different way. We just continue this process. We just keep going. We keep making generations and generations of fish who know exactly how to get to a certain point, and then from there on, they just have to leave it to chance to see if they get more than 50% of their peers or not. And finally, we have some kind of path, some kind of genetically defined path to get from the birthplace to the ending place of these fish, and hopefully it'll give us some kind of local optimum. And I'll define what I mean by local optimum in the amount of food that they get before they finally die. So we're going to go to the computer program in just a second, and it'll all become a lot more interesting. But first, let's look at 2 different definitions, which are going to help us a little bit later on. So the first definition will be the genetic path, and the other definition will be the optimal path. The genetic path is exactly what we've been talking about. It's the path you get when you repeat this process over and over and over again. You start with a certain amount of fish. It doesn't have to be 90. You can have even more. In the program, we'll have 1,000, so it'll be even bigger sample size. But you have a certain amount of fish who start as infants right here. And then you just keep doing this. You just keep taking the top 50% at each generation, and you find some kind of locally optimal path to get to the end. So it turns out in this example, the genetic path, the path we get from doing this process over and over and over again until we get to the very end, is this path right here. So it starts here. The infant fish starts right here. We capture this 3, we capture this 3, we go up, we capture this 2, we capture this 2, we go over, capture this 2, go up, and go like this. And that ends up being the optimal path for this lake right here. And let's count. How much does that end up being? If we add up every single point, all these pieces of food here before the fish ends up getting to its final resting place, we get that the genetic path gives us 20 pieces of food. Now, how do we know that that's the best? Is that the best? In fact, it's actually not. Here's the very interesting thing about this. Let's look at this path right here, the path that just goes on the perimeter right here. So let's look at this swim, where if a fish were to take this 1, which is something that we wouldn't really want to do under the genetic method, and it goes up like this, and it goes over like this. How much does that give it? Well, 1, 4, 7, 9, 12, and then these last 9 give you 12 plus 9 is 21. So actually, 21, there's a better swim than the genetic swim. But why wasn't it picked? Why didn't our method pick it? Because to do the swim, you initially have to pick up 1 piece of food. And what happened to all the fish who initially picked up 1 piece of food? They were all just left behind and killed off, and they didn't get taken by the rest of their peers. But if they were taken with their peers, a few of these brave souls would end up finding their way all the way to here and get 1 more piece of food than all the other fish, than the optimal fish under the genetic method. So this is actually pretty interesting. Let's go to the computer program now and see what we get using a much bigger lake, a 10 by 10 lake. So now that we have some more computing power behind us, we can look at a bigger example. So without further ado, let's go ahead and run this. So as we said, we have the lake first. Each piece of the lake, each spot on the lake has either 1, 2, or 3 pieces of food, just as we had with the 5 by 5 example. And we see this 0 right here because that's where the fish starts, and we just marked it as 0. Now how you interpret these other 2, so the genetic swim and the optimal swim are the same thing as the genetic path and the optimal path that we said on the previous piece of paper. All these zeros are positions that are untouched by the path, and all these numbers that are retained, which you see are the same numbers that are in the lake, they basically outline the path that is taken. So for example, in this genetic swim, we find that the fish starts here, as always, in the lower left-hand corner. It goes up, it goes over, it goes up, it goes over, up. It does a diagonal move right here. We see it goes from this 2 to this 3 right here. And then it goes over a few more, it goes up, and it goes over until it finally reaches its final resting place. Now, what was the score of that genetic swim? Which is basically, if we add all these numbers together, we see the genetic score is 47. Now, if we do an optimal swim, and if you want a link, I'll put another video of how we get this optimal swim. It's pretty interesting as well. So click right here for how we get that optimal swim. You can watch that. But anyway, the optimal swim, we get how much? So first of all, the optimal swim is a little bit different. It goes up, it goes over. We see it starts just like the genetic swim. It goes up, it goes over like this, and then things start to deviate a little bit until it finally gets to the end. We see that the maximum score, if we add all these numbers together, is 49, which is 2 more than that 47. And this average percent correct we see right here is basically just dividing this 47 by 49 to tell us basically how correct the genetic score is in relative to the maximum score. So let's do this one more time. We'll do another random lake. We'll run it again, and we have another random lake. So in this lake, we see that, these numbers are different. They're still between 1, 2, and 3. The genetic swim is, you can just outline it. You can see how it goes. The optimal swim is actually, in this case, the exact same as the genetic swim. So we can see that also because the genetic score and the maximum score are the same, giving us an average percent correct of 100%, so we actually got kind of lucky in this case. But, we don't want to do this just sample by sample, seeing what accuracy we get. So what we're going to do is we're going to run this 100 times, taking 100 different random lakes, 10 by 10 lakes, and we're going to take the average of all the accuracy values to see what's the true accuracy, or pretty close to the true accuracy of this genetic method. So what's going on right now is that it's just going through all these different lakes, and we find that after all that, the average percent correct is about 94%. So what that's saying is, on average, the genetic score is 94% of the maximum score, which is pretty good for a algorithm that is not guaranteed to be correct. It gets pretty close to the true correct value, and it seems acceptable in many cases. So all of the silliness with the Sillyfish was just really outlining an algorithm method called genetic algorithms, or genetic programming. And all that it really is, genetic programming, is that you start with a huge subset, a huge sample of just objects. So in this case, our objects were Sillyfish. And you have some goal in mind. So with genetic programming, there has to be some final goal. So our final goal was to reach this top right-hand corner. And these objects have no idea whatsoever how to reach their goal, and they end up, in the beginning, they just start doing things randomly. But with that randomness comes the natural case where some will do better than others in the beginning steps. And we keep those that do better, and we throw away those that don't do as well, in the hopes that by keeping those that do better and just creating duplicates of those who do the same initial steps and then do some more random steps, and then we keep those who do the better in the next generation, and we just keep going like that, and we just keep basically reproducing those who are getting the best scores at each intermediate step, we hope we'll reach some kind of optimum. It's not always, as we saw, going to be the exact optimum, as we saw with this whole 21 being bigger than 20 situation, but as we saw also with that 94% accuracy, it's going to be pretty dang close in many cases to the optimal we can get. And another advantage of this is that this requires a lot less thinking in the case that we don't need to know the exact way to solve this problem. We don't need to think too hard about the exact algorithm. We can just run the genetic algorithm. This took no thinking at all, right? I had no idea how to solve this problem. I just let these fish loose and just kept doing this process of, hey, did you make it past the 50% mark? Yes. Okay, we'll keep you for the next generation. We'll make more like you, so maybe they'll even do better than your generation did, and so on and so on and so on. And we ended up reaching some kind of solution that was just one off from the optimum solution. So it's really a trade-off of how much time you want to spend on the problem versus if you just want to get something that's locally optimum. This also is a little bit of commentary on natural selection. Of course, natural selection is not perfect. There's probably always a way it could have gone that would have made things much better for any species. But this example, I understand this is a very micro example, and natural selection is a very complicated process, but this kind of comments on the fact that natural selection has a local optimum kind of nature, which, maybe is good enough for most species that are around right now. So until next time.